Welcome to Lecture 16 of CS 182. In today's lecture, we're going to continue our discussion of reinforcement learning and learn about actor-critic algorithms and Q-learning methods. So, to recap from last time, on Monday, we learned about policy gradients. The classic policy gradient algorithm, called reinforce, consists of 3 steps. Sample trajectories by running your current policy. Evaluate the policy gradient by averaging together the sum of grad log pi's and rewards, and then take a step in the direction of the policy gradient. So you can kind of think of it as having 3 steps: generate samples, estimate rewards, and then improve the policy. Where the estimate of the reward, these Q hats, are just given by summing together the reward from the current time step until the end, and the policy improvement is a gradient step. So remember that we use this symbol Q hat to denote the reward to go, the sum of rewards from the current step t until the end. It's this reward to go term that we're going to focus on in today's lecture. There's actually quite a bit you can do to estimate this term much more effectively than is done in reinforce, and this leads to a much more powerful class of algorithms. So let's talk about how we can improve the policy gradient. Q hat is an estimate of the expected reward if you take action AT in state ST. And the better this estimate, the more accurate your policy gradient will be. In the regular reinforce algorithm, this estimate is obtained by summing together the actual rewards that you obtained from time step t until the end. But those rewards lie along only one possible trajectory that you could have followed after that time step. Can you get a better estimate? So in reinforce, you generate a trajectory, and then if you're trying to estimate Q hat at a particular time step, you're basically summing together the tail of that trajectory, which is a very reasonable thing to do. However, in reality, if you were to find yourself in that same exact state again and take the same exact action, you might get a different outcome simply because everything that happens afterwards is stochastic, right? So estimating Q hat just by summing together the rewards you got is not the best estimator that you can get. The reality is that there are many other possible futures that you're not accounting for when you do this. Mathematically, this sum of rewards is what is called a single sample estimator. You're essentially estimating some integral over all possible outcomes using a single sample. It's valid, meaning that it is asymptotically consistent, but it is not the best estimator you can get. So what you really want is you want the expected value of the reward that you'll see from now until the end. But of course, computing those expected values exactly is impossible. But if you could somehow get them, then you would have a better estimator. You would actually be accounting for all the possible futures that might occur, not just a single sample. Intuitively, the place where this might become really important is if you took some action and then you got a high reward. But maybe you got that high reward because you got lucky. Maybe your action was to buy a lottery ticket and you got a high reward for buying that lottery ticket. Well, chances are if you bought the lottery ticket again, you wouldn't win again. If you had enough samples, eventually you would see this. But if you had just a few samples and you got lucky, then you might erroneously think that buying the lottery ticket is a good idea. If, however, you had a better estimate of the reward to go, you might be able to figure out that the expected value is not so high for that action. All right. So if we somehow had a better estimate of the expected reward to go, let's call it Q instead of Q hat, then we could simply substitute it in place of Q hat and get a better policy gradient estimator. So what we'll discuss next is ways that we can estimate this expected value that are better than simply summing up the rewards along the trajectory that you actually got in reinforce. Now, what about the baseline? So the policy gradient expression I had before didn't have a baseline, but we learned last time that baselines are really important. So in reality, you would want to multiply grad log pi by Q minus B. And which B should you use? Well, you should use the average reward. And in particular, it's actually very convenient if you average the reward over all possible actions in that state. So if you average the different Qs. And of course, the right way to average them is to take their expected value under the policy. Now here, your baseline will depend on the state. It turns out that that's actually still unbiased. I'm not going to go through the proof for that, but it's actually fairly straightforward to show. And now, your coefficients on these grad log pi's will be QSA minus VS, where VS is just defined as the expected value under pi of QSA. We call these differences Q minus V advantages. The advantage describes how much better is the action A in state S than the average action. And the value of the average action is given by V, because V is actually just the average over all the actions weighted by their probability under pi. So ASA describes the advantage of action A in state S, which is how much better is the Q value, the Q function value of SA, than the average value at state S given by V of S. Okay, so let's just formally introduce this terminology. QSA is referred to as a Q function, and it tells you the total reward that you'll get from taking action AT in state ST in expectation. And really we should write it as Q pi, because the Q function depends on the policy. It's the Q function for a particular policy. It is the expected reward that you will get if you take action AT in state ST and then follow the policy pi. The value function, V pi of S, is just the expected value of the Q function where the actions are distributed according to the policy pi. But that also means that the value function is the expected reward that you will get if you start in state ST and then follow the policy pi. The advantage function is just the difference. How much better is AT than the average action in state ST? And the policy gradient is given by the gradient of the log probability of an action multiplied by its advantage. And the better your estimate of the advantage, the better your estimate of the policy gradient will be. Of course, you don't know exactly what the advantage value is. You can't compute these expectations exactly, but you can approximate them in many different ways, many of which are much, much better than simply summing together the rewards that you saw along a single sample. So the better the estimate of A, the lower the variance of your policy gradient, and the more accurate your policy gradient will be. So the old policy gradient that we saw is simply a single sample estimate. It's a version of this more general equation in the middle where Q is given by sum of rewards and V is given by just a single scalar value, which of course are not very good estimates. It's an unbiased estimate, but it's high variance, meaning that you need a large number of samples to get an accurate estimate from it. So if we go back to this picture that we saw before, what we're going to do is we're going to maintain the overall structure of the policy gradient algorithm, but we'll change how we estimate the return. Instead of just summing together the rewards, we'll actually fit a different neural network, a separate neural network, a second one, to estimate either Q pi or V pi or A pi. So we'll have two networks now, a policy network and a value function network that we'll use to estimate these advantages. And that will give us what are called actor-critic algorithms. Okay, so what can we do? We've got three different objects, Q, V, and A, and they're all related to one another. The one that we ultimately want is A. But if we're going to fit a separate neural network, we can ask, well, what do we fit it to, and what do we fit? So fit what to what? We can fit an estimate of Q pi or V pi or A pi. Q pi is the expected reward, which you can also write as the current reward plus the expectation of the future reward. Now this expectation of the future reward is exactly the value function. So you can write your Q function as the current reward, because that ST and AT are not random variables, plus the expected value of the reward of the value function at time t plus 1. So this is sometimes referred to as the Bellman equation. It's one of the most fundamental recursions. Let's just go through it again to make sure it's all clear. Notice that Q pi is a sum from t prime equals t to capital T of the expectation of the reward. All ST primes after time step t are random variables, but ST and AT are not random variables. They're actually arguments into this function. So you can equivalently write that sum as the current reward R of ST-AT, which is not an expected value because ST and AT are not random variables, plus the expectation of all the stuff in the future. And you know that the expectation of all the stuff in the future is perfectly summarized by the expected value of V pi ST plus 1, where ST plus 1 is distributed according to P of ST plus 1 given ST-AT. And that means that you can form a really good approximation to q pi st at by taking the actual state st plus 1 that you saw along your trajectory. This is a single sample estimate of st plus 1, but it's not a single sample estimate for the rest of the trajectory because you're still using v pi. So you get a little bit of approximation error from doing this, but only a little bit. However, this is very, very convenient because that means that if you want to write out the advantage, you just subtract v pi st from this, so that means that the advantage is equal to r st at plus v pi st plus 1 minus v pi st. So that means that you can express both the advantage and the q values in terms of just the value function. And the value function depends only on the state and not on the action, so it should be easier to fit because it has fewer inputs. So for that reason, classic actor-critic algorithms typically fit the value function. Although it is quite possible, and we'll discuss this later, to have actor-critic algorithms that fit the q function instead. So what we're going to do is we're going to have another neural network that takes in the state as input and outputs an estimate for the value. So it takes in a state and outputs a scalar value. And we're going to use this network to compute these advantages, which we'll then plug into the policy gradient. And just to keep the notation straight, we'll say that theta represents parameters of the policy and phi represents parameters of the value function. Fitting the value function is sometimes referred to as policy evaluation, because when you fit the value function, you're not trying to make the policy better just yet. You're just trying to figure out how good it is. You're trying to find its value function. Once you've found its value function, you can then use it to improve the policy. By the way, remember that the reinforcement learning objective is just the expected value of the total reward starting from the initial state, which is also exactly equal to the expected value of the value function on the initial state. So if you can compute the value function, you can also evaluate the value of the reinforcement learning objective. All right, so how do we perform policy evaluation? Well, one very simple thing to do is what's called Monte Carlo policy evaluation. This is basically what policy gradient does. We've already learned about this, we just didn't use this name before. So Monte Carlo policy evaluation is when you actually generate samples from your policy, run them, and see what the total reward you get is. So in this case, you would want the value at a particular state to be approximately equal to the sum of rewards starting at that state until the end. So if you just sum together the rewards and the tail of the trajectory, and you use those as labels for the value function at that state. If you had multiple samples, you could sample the reward along multiple samples, but typically you can't do this because you can't teleport to a state that you've seen before on another trajectory and then roll it out again from there. You can teleport back to the initial state. That's what you get when you generate a sample, but you can't teleport to an intermediate state. So if you wanted a multi-sample estimator, you would have to use a simulator where you can reset to an arbitrary state. So usually you wouldn't be able to do this. Okay, but you can't have the single sample estimates. So can we have Monte Carlo evaluation with neural net function approximation but single sample estimates? So your neural network is going to take in S and it's going to output a scalar value, which represents your estimate of the value function. The way you're going to generate labels is that you're going to take all the states you've seen along the trajectories you generated by sampling, and you're going to, for every state, you'll sum together the rewards from that time step until the end and use those as your label. But remember that you might have multiple trajectories that have states that are close together. They're not going to be perfectly identical, but they might be close together. So it's still a good idea to learn a value function even though you're using a single sample estimator, because your value function might assign similar values to nearby samples that are not exactly identical. So if you have two nearby states that have different labels, but they're very close together, chances are your value function will actually average out their values. And that's just the effect of having function approximations, because neural nets will try to represent functions that are somewhat continuous. So it's not as good as having multiple samples from every state, but it's still pretty good. So formally, the way this method works is you generate your sample trajectories, and then for every state you've seen, you label that state with the total reward from that time step until the end. And we'll call those target values YIT. And then you simply train your model with gradient descent on a supervised regression loss, on a mean squared error loss. So your loss is just the average over all the states that you've seen of the predicted value at that state minus the label value YIT. So it's just a regular mean squared error regression problem. And that will actually get you better value function estimates, better than what you would get by directly plugging in those sums of rewards into policy gradient, because your value function, the neural net representing your value function, will do some averaging. It'll average together the values of nearby states, which will reduce the effect of those lucky outcomes or unlucky outcomes. But you can do much better. So far we learned about these Monte Carlo targets, where you just take a single sample sum. The ideal target is a full expected value. Now, these full expected values, as we saw before when we described how Q functions and value functions relate to one another, can be written as the reward right now, RSTAT, plus the sum from t plus 1 up to the end of the expected reward at that step. And remember that our value function is directly trying to estimate expected rewards. So if we knew v pi, we could compute better targets as the current reward plus the next value. Now, of course, we don't know v pi. If we knew it, why would we be learning it? But what we can do, and this is called the bootstrap, is to approximate the v pi at the next time step by our current value function. So essentially, the value function will be learning from itself. We'll say that the expected reward at time step t is the reward that you got right now, plus our estimate of the expected reward in the future, which we get from our own value function. So we can directly use the previous fit value function of input. So now our training data will be obtained by rolling out some trajectories, taking every state we saw and then labeling it with the reward at that time step plus the value function at the next time step, where the value function is just the previous value function that we fitted to our previous data. And that's now our target value YIT. And we fit that, again, with supervised regression. So this is sometimes referred to as a bootstrapped estimate. And it might seem a little peculiar because we're just using our own value function again, but it actually ends up working much better if implemented properly. It can be harder to train, it can be harder to set it up so that it's stable, but if it can be made stable, it tends to work a lot better. All right. Now, value functions, the value functions that we get from policy evaluation, they actually have some fairly intuitive interpretations sometimes. For example, this is from an old paper called TD Gammon back in 1992. Here, the goal was to learn value functions for playing the game of backgammon, and the reward was 1 if you win the game and 0 otherwise. In that case, the value function, the expected reward, is just the expected, it's just your expectation about whether you win the game. So the value function is a function of the board state, and it's literally you look at the board state and your value function outputs how likely it thinks you are to win given this board state. So it has a very intuitive interpretation. The reward is the game outcome, the value function, the expected outcome given the board state, which is basically your probability of winning. In AlphaGo, the same exact idea was used. So even though it came decades after TD Gammon, it was essentially the same principle. The value function is an evaluation of the board state, which is your probability of winning. Okay, so now that we've talked about how we can estimate value functions, we can derive a full actor-critic algorithm that actually uses these value functions to improve the policy gradient. So the term actor-critic refers to the fact that we have two neural networks now. We have the policy, which is the actor, it's the one that actually acts, and we have the critic, that's the value function, and it essentially criticizes the policy, tries to estimate its value, tries to evaluate it. The structure of the batch actor-critic algorithm is pretty similar to the structure of reinforce, with the addition that we're going to be training these value functions. So we sample trajectories by running the policy. We fit the value function at step 2 to our sampled rewards. In step 3, we evaluate the advantage for every state action tuple that we've seen. And in step 4, we estimate our gradient by multiplying the grad log pi's together with the advantages. Now, something to note about the way I wrote this out, at this point, I'm no longer differentiating between whether states occur in the same trajectory or not, because this algorithm actually doesn't care. All it needs is state, action, next state. It doesn't care whether things participate in the same trajectory or not, because everything is bootstrapped. Basically, we never need to see more than 2 sequential states. Of course, in reality, you still sample entire trajectories, but then you can pull out essentially state, action, next state tuples out of those and use them to fit the value function, evaluate the advantage, and evaluate the policy gradient. So you can fit your value function to sampled rewards, You can do it using Monte Carlo, but it's better to do it using Bootstrap, so that'll work better. And you fit them with mean squared error, and then you use them to estimate those advantages. All right. Now there's an important aside that I have to discuss next. There's a little problem with how I've explained the bootstrap so far, because those of you that were paying very close attention might have noticed that each time you update the value function, you take your previous value function and you add something to it. So if your rewards are always positive, let's say, it doesn't matter what they are as long as they're all positive numbers, your target values will keep getting bigger because you're always adding stuff, you're never subtracting. So what if your episode length is infinity? Won't you eventually just sum up an infinite number of values? That's actually a big problem because in this case, your value function might become infinite. There are some cases where finite episodes are very natural, like for some robotic tasks. But oftentimes it's much more natural to have continuous or cyclic tasks where, let's say, you want to get this little humanoid robot to run as far as possible. So here your horizon is really infinite. And that's a big problem because now your values will become infinite. So there's a simple trick that you can use to handle these kinds of cases. And this trick is, again, almost always used in practice. The trick is that you prefer to get rewards sooner rather than later. That's very intuitive. If I tell you that I'm going to give you $10, maybe you're pretty happy about that. If I tell you that I'm going to give you $10 in a month, okay, you're probably still happy, but not as happy. If I tell you I'm going to give you $10 in a year, maybe you won't take me that seriously because in a year, who knows what's going to happen. If I tell you that I'm going to give you $10 in 100 years, you probably just don't care because you're not going to care very much about what happens in 100 years. So we can get our agents to think the same way. We can get our agents to prefer rewards sooner rather than later. And the way we do that is by slightly modifying this target value. Instead of taking the reward and adding the value function, we take the reward and add the value function multiplied by a small constant gamma. And gamma is going to be a number that is close to 1, maybe like 0.9 or 0.99. And that essentially discounts the rewards in the future by a little bit. 0.99 works well. What's the meaning of this discount factor? Well, its meaning is actually very similar to the intuition behind why you might not care if I promise to give you $10 in 100 years, which is that, things change in 100 years. People die. Maybe you won't be around to enjoy those $10. The agent can think the same way. You can have some probability. You can take your original MDP and you can add an additional state, which you can call the death state. And there's some probability that you would enter that death state at every time step, essentially the probability that you would die. And that probability is 1 minus gamma. And we just add a transition into the death state with probability 1 minus gamma at every time step. Which means that your probability of staying in the MDP, of not dying, is gamma. So the probability of dying is 1 minus gamma. The probability of not dying becomes the old probability times gamma. And since the value function should really be taken in expectation under the transition probabilities, you can safely multiply it by gamma to account for the probability of staying alive. So that's the intuition for why you can add this gamma discount. In practice, we would almost always do this, and we would use gamma values of 0.9 or 0.99. So you can think of this as just encoding a preference to have rewards sooner rather than later, or you can think of it as encoding the probability that the agent might die at any given time step with some low chance. Okay, so here's the Actor-Critic algorithm with the discount. We can also write out a fully online version of the Actor-Critic. So with these bootstrapped value estimates, we actually only need to know the next state in the trajectory. We don't need to know all the rest of the states, which means that we can update the critic and the actor every single step rather than waiting to collect a batch of trajectories. So a fully online Actor-Critic algorithm would take a single action from the policy and then actually take that action in the world and see the resulting next state S prime. So we get a tuple SAS prime R. Then it would update the value function using the reward that it got plus gamma times the value at S prime. So that gives you one sample for stochastic gradient descent. Then it would evaluate the advantage using that value. Again, this only uses SA and S prime. And then it would use that sample to take a gradient step on the policy. And again, that only uses a single sample, so that effectively implements stochastic gradient descent. So if you're willing to do single sample stochastic gradient descent, you can actually have a fully online actor-critic algorithm that updates both the critic and the actor every single time step. So it learns continuously. Now, in reality, SGD with just a single sample is not a good idea. It's not going to be very stable. So in practice, when people implement these online actor-critic algorithms, they usually have some kind of multi-threading process where they have multiple threads, each collecting a single sample, and they average over those threads to get a mini batch. We won't cover that in this class, but if you're interested in this, you can look up something called asynchronous advantage actor-critic, which basically implements this procedure. Okay, a brief remark about neural net architectures for actor-critic. We have these two networks that we have to implement, a critic network and an actor network, V and pi. We have a few choices to make. A very simple choice is to actually have two separate neural nets. One neural net maps states to scalar valued values, and the other network maps states to distributions over actions. That's probably the simplest design. It's simple and stable, but it can be a little inefficient because there's no sharing of features between the actor and the critic. Intuitively, the information that you need to evaluate the value is probably pretty similar to the information that you need to run the policy. But since these are two totally separate networks, they're not allowed to share that information. So a more advanced design, a shared network design, is one where, and I apologize that it's cut off on the slide, but it's one where you have a single neural network with two separate heads, one head for the value and one for the policy. And that allows you to share representations, but can be a little bit less stable to train.